We're going to continue talking about NMR, nuclear magnetic resonance spectroscopy. And I don't know how many of you have watched the video I posted about it, and so we'll just sort of start at the beginning and get as far as we're going to go. This is an analytical technique for understanding or really figuring out the connectivity of organic molecules. This is really how we know what the product of a reaction is. And we're going to talk a little bit about how it works, but for the most part, you don't need to understand need to understand the physics for how it works in order to be able to use it. But the basic principle is that protons and neutrons have a quantum property called spin, and that some nuclei have net non-zero spin. So some protons and neutrons are somewhat like electrons. They can have a spin property. It just so happens that proton, hydrogen, and carbon-13 are both spin 1/2 nuclei. And what that means is they can exist in two possible spin states, either plus 1/2 or minus 1/2. Now, that doesn't necessarily matter for our discussion, other than we're going to think of protons and carbons as being little magnets that can respond to an external magnetic field. So what I'm attempting to show you here is there are two spin states for, say, a proton nucleus. And we're talking here about the nucleus, not about the electron. It can have either plus 1/2 or minus 1/2. In the absence of a magnetic field, those spin states are equal in energy. But if you apply an external magnetic field, the two spin states split. One is lower, one is higher. You can think of the lower energy one as the one that's being aligned with the magnetic field, and the higher energy one is the one being aligned against the magnetic field. And there is an energy difference between these two spin states. The weird thing is that energy difference is really, really, really small, like less than around 0.1 kilocalories per mole, which means that even in an external magnetic field, you've basically got a 50-50 mixture of spin states. However, if you do the math, that 0.1 kilocalories per mole, and then you use Planck's constant, you figure out what kind of frequency a photon would cause a transition between spin states, and it's in the radio frequency range, 300 to 900 megahertz. So we have an instrument downstairs that has a strong magnetic field. It's an electromagnet. And then there is a probe that shoots radio frequency energy at the sample and causes a transition among protons from a aligned with the magnetic field state to aligned against the magnetic field state. And we can actually measure the frequency of the photon that causes that transition. Okay, big deal. We can see that a proton's there. Couple of things. Different protons in different environments will undergo spin flipping at different frequencies. And that's the key then. Unique protons in unique chemical environments will have unique frequencies, and therefore we can detect them and analyze the structure of a molecule. Now these numbers are really high. You can either have it in scientific notation or megahertz, and so it's become traditional to normalize this frequency at which a photon can transition a proton from being aligned with to against the magnetic field, to normalize that into other more easy to use terms. The difference in energy between these two spin states depends on the strength of the magnetic field. The stronger the magnetic field, the bigger this difference, and so the larger the frequency. And of course, different universities have different spectrometers with different magnetic field strengths, and so to facilitate comparison from site to site, we can take the frequency that a proton resonates at, we'll subtract a reference proton frequency, and then divide it by the reference proton frequency in megahertz, and we end up with something called a chemical shift. You don't need to know any of that other than the chemical shift, which is indicated by this Greek letter delta, relates to the frequency at which a proton undergoes spin flipping. So larger magnetic field means larger energy difference. Larger energy difference means higher frequency, and then higher frequency relative to some reference means higher chemical shift. All right. So different protons, chemically distinct protons, have different chemical shift values because they experience different environments. So we're going to talk about how the environment of a proton influences chemical shift. A good rule of thumb is the more electron-rich an area is where a proton is, the lower its chemical shift is going to be. The reason for that is that, as you know from physics, in the presence of a magnetic field, electrons move, right? And it just so happens that the electrons that surround a proton will move in such a way as to create their own magnetic field that opposes the external magnetic field. So if you wanted to, we could get really deep into right-handed rules about if electrons move in this direction and then the field lines are this way, and then you have to remember, oh wait, it's not where the electrons move, it's current, which is opposite electrons, and that's all crazy. What we want to say, though, is that in the presence of this external magnetic field, electrons will tend to circulate in a way that creates an induced magnetic field that opposes the external magnetic field. So this little lowercase b sub I means the induced magnetic field that the electrons create in the presence of this external magnetic field. So if we ask ourselves, what kind of magnetic field does this proton experience? It experiences the external magnetic field and then subtract the induced magnetic field. So what it experiences depends on its environment, and the presence of electrons in the environment will tend to reduce the extent of the external magnetic field that a proton experiences. And then that's going to make its chemical shift lower. We call this phenomenon shielding. All right, so the presence of a lot of electrons tends to shield the proton from the external magnetic field, and the shielding moves you to lower values of chemical shift. Questions so far? Yes?
I don't know if I can articulate this, but if the thing that's shielding is induced by, like, the thing that's causing the shielding is then being shielded.
Yeah.
I don't know.
It sounds a little bit circular, right?
Yeah.
It just has to do, well, so the thing that is experiencing the field is the proton. The thing that's doing the shielding is the nearby electrons. And the reason they're doing the shielding is because of the external magnetic field. Which you apply. This is the external magnetic field is the thing that the instrument does. There's this supercooled electromagnet that creates a strong field worth X number of Teslas, and then that creates that causes electron motion to oppose the magnetic field. Okay. Others? Yes.
So do we need to make magnets or VOs that have both positive and negative spin?
Do you need to make external magnetic fields that have positive in a positive/negative direction? No. The thing that will have plus or minus spin is the proton. The external magnetic field that we apply will just be in one direction.
Okay, so we're only ever going to observe one of those types, so like the protons with negative spin, because they'll always be against this field?
So in the presence of the external magnetic field, half of the protons are going to be aligned with and half are going to be aligned against, and there will be an energy difference between the two.
Okay, but like what if there's an odd, even just one proton?
What if there's an odd number of protons? Let me...
Like looking at a molecule, can you tell which ones are positive or negative?
Oh, looking at a molecule, can you tell which ones are plus or minus spin? No.
What's the connection?
And in fact, this is in a population of molecules, some of the protons will be aligned with, some will be aligned against. The thing that we're doing is we're shooting a photon at the system to cause a transition from plus to minus. And we can observe that, and then the frequency at which that occurs will tell us something about the environment of that proton.
Okay.
So, yeah, you're just looking at, in a sense, you're looking at a huge population of protons. Over here we have the spin plus 1/2 population. Over here we have the spin minus 1/2 population. And there's like, gazillions of these, and then there's gazillions of these. And if we shoot a photon at the appropriate frequency, we will cause one of these perhaps to shift. And we can observe the frequency of light that causes that to happen. Right. Okay, others? Okay, so there are situations where, so this is in general, protons in an electron-rich environment will be shielded. So what are electron-rich protons? You're thinking like alkanes, just regular CH3 or CH2 kind of protons, or protons that are not near an electronegative group. You could imagine that an electronegative group, such as oxygen, would tend to pull electron density away from the protons because of electronegativity, and that would cause the protons to be even more electron poor. So if you compare the following two situations, methane versus some ether or alcohol, the proton here will have a chemical shift of about 1 part per million. That's the units of chemical shift, 1 ppm. You don't need to worry about those particular units, but a proton that's adjacent to an electronegative atom will show up around 3 or 4 ppm. Lower frequency, lower experienced magnetic field because of the shielding that's experienced by this proton due to the presence of nearby electrons. Higher chemical shift because it experiences a larger magnetic field because it's less shielded because the oxygen's pulling electron density away from those protons. Okay, so electronegativity is going to help a lot in interpreting NMR chemical shift information. If you're in an electron-poor environment, your chemical shift should be higher. If you're in an electron-rich environment, your chemical shift should be lower. Okay, there are a couple of unique situations where the induced magnetic field actually causes the proton to experience a greater magnetic field, but those situations are rare. So the one situation we're going to be aware of is in protons that are attached to aromatic rings. So here, and again, don't worry about scribbling all of this down because you're going to have the notes, but here is a benzene ring, and the pi electrons of the benzene ring are we haven't talked about pi orbitals in a benzene ring, but you'll learn about that in 352. They're delocalized across the whole ring, both above and below the plane of the ring. In the presence of a magnetic field that you apply, those electrons can circulate in a much more extensive pattern, and that circulation opposes the magnetic field in the center of the ring, where there aren't any protons, but it reinforces the external magnetic field outside the ring. I've drawn the magnetic field lines. That's all the physics I know about this, and I'm sorry. But the protons that are outside on the edge of the ring are in a de-shielded environment because they experience not only the external magnetic field, but also the induced magnetic field. These protons are said to be de-shielded. They experience a larger effective field. They spin flip at a larger frequency, higher chemical shift. And protons that are adjacent to benzene rings tend to have chemical shifts around 7 ppm. All right. Let's see. So the general principle is protons in electron poor environments are de-shielded, protons in electron rich environments are shielded. So now I'm just going to give you a brief tour of the kinds of chemical shifts we experience of different kinds of protons. Ultimately, your goal is going to be able to get data from an NMR experiment and solve the structure of a molecule. So, I told you before, alkyl protons tend to be around 1 ppm in chemical shift. By the way, you don't have to memorize any of these. There will be a table on the exam, I think. Should we verify that? There will be a table on the exam that gives you chemical shift information. I'm opening up the final exam on my screen here. Should I just drag it over? You can see it. Just going to confirm that you have a chemical shift. That's really rude, right? I'm taunting you. Yeah. Anyway, we'll verify. I'll show you actually what the table is going to look like. All right, so you're going to have A values, you're going to have pKa's. Here's a chemical shift table which tells you where to expect alkyl versus other kinds of protons. Okay, so you're going to have that. You'll also have some IR functional group information. Anyway. Yes?
What is the A value again?
A value tells you how sterically big some group is. Yeah. No, A value tells you the difference in energy between having a group axial versus equatorial. Yep. Here's a problem on the exam.
But you're not telling us. Oh, yeah.
Yeah. Oh, look, that looks like a problem from exam 1. Looks like you're going to have to know pKa information. Look what you told me the other day. Yeah, exactly. Okay. That was your hint. Also, you should be able to sign R and S and E and Z. That'll be useful. Okay. So, types of chemical shifts, environments that you can, or rather ranges of chemical shift that tell you something about the environment of a proton. In the range from 1 to 2 ppm, you tend to see alkyl protons. Now, there is a trend where secondary protons on secondary carbons versus tertiary carbons are a little less shielded than protons on primary carbons. That's a trend, but it's not that useful for you. So you don't necessarily need to worry about that. But this is where your run-of-the-mill hydrocarbon proton shows up. Another situation is protons that are alpha to pi bonds. Okay? There is some electron circulation in a pi bond that causes some de-shielding in the immediate vicinity of the pi bond, but in the range of about 2 ppm, you tend to see protons that are alpha to pi bonds. So this can be alpha to a carbonyl, alpha to an imine, that's a functional group that you'll learn about in 352. You can be alpha to just a regular olefin, or you can be alpha to a benzene ring. And you show up in this region of around 2 ppm. Also, being a proton on an alkyne carbon gets you in the same sort of area. As I said before, if you're alpha to an electronegative atom, such as oxygen, nitrogen, fluorine, chlorine, bromine, and so on, you tend to be in the 3 to 4 ppm region. Now, there's a tricky area here, protons that are on electronegative heteroatoms. Their chemical shift can basically be anywhere. And the reason for that has to do with hydrogen bonding. So we're going to talk about one practical issue that we're not going to spend a lot of time on is the fact that when you do an NMR experiment, if you want to see protons in your sample, the solvent you use must not have hydrogen protons in it, because if it does, that will totally overwhelm the signal from your sample. So we tend to use solvents that have deuterium instead of proton. One example of a solvent that's often used is CdCl3, or deuterated chloroform. There are other solvents, for example, CD3OD, which is deuterated methanol. If your solvent has, like deuterated methanol here, if your solvent has a bond between oxygen or an electronegative heteroatom and deuterium, that deuterium here can exchange with this proton there via hydrogen bonding. We talked a long time ago about hydrogen bonding and how it's really sort of very flexible as to which proton goes with which oxygen, and they can trade a lot. If you're using a solvent that has if you're using a solvent that we would call a protic solvent, that is one where you have a bond between an electronegative element and deuterium, then likely you will not see an alcohol or amine proton at all, because it will exchange with the solvent. And again, the NMR experiment detects protons. The kind that we're going to use detects protons and not deuterium. So you may or may not see protons associated with OH or NH groups. What that often means is you're going to have to detect the presence of an OH or NH group indirectly by looking at the chemical shift of a nearby hydrogen. Continuing on, protons attached to sp2 carbons tend to be in the 4 to 6 ppm region. Amide protons tend to be in the 6 to 8 region. Protons adjacent to benzene rings tend to be 7 to 8. Protons on aldehydes, 9 to 10. And then carboxylic acids are usually the most de-shielded of the protons that we look at. Some of these effects are additive. So, for example, you would expect these two protons that are alpha to 2 carbonyls to be more de-shielded and have a higher chemical shift than protons that are alpha to just 1 carbonyl, and so on. All right, so that's chemical shift, which tells us about environment. All right, questions so far? Okay. We need to deal with one issue that sort of goes back to stereochemistry, and that is protons that are identical by symmetry, that have identical environments, have to have identical chemical shifts. So the tools you used in Chapter 5 for identifying stereocenters are going to apply here as you identify which protons are different. For example, in this benzene ring, there is only one kind of proton, because purple proton is exchangeable with any of the orange protons by an element of symmetry, right? There's a mirror plane here. This proton is the same as that one. There's an axis of rotation here. Do steering wheel action by 60 degrees and we exchange, or maybe it's 120, I don't know. We exchange one proton for another there. Protons that are identical by symmetry must have the same chemical shift. So if you took an NMR spectrum of benzene, what you would see, this axis would be like, I don't know, intensity or whatever. We don't even need to define it. This axis would be chemical shift. And around 7 ppm, we would see a single peak. There would just be one NMR signal for that molecule because there's only one kind of proton in that molecule. Similarly, I mean, we can do all sorts of we can look at all sorts of different symmetry operations. In chloroform here, the 3 methyl protons are identical because you can interchange them by rotation. Okay? In propane, the 2 protons here are identical to each other because of a mirror plane of symmetry that's in the plane of the page here. You can interchange each of these purple protons with each other. Similarly, methyl protons here are identical to methyl protons there, again by symmetry. Another example would be how many different kinds of protons do we have in this alcohol? We have 3. The methyl protons, the 2 CH2 protons are identical to each other, again because of a plane of symmetry, and then the alcohol proton is distinct. Yeah?
So on the graph, for this example, would we see 3 peaks?
Yes, you would expect to see 3 peaks in the graph for in the NMR spectrum. You would expect to see a peak for the methyl group. That methyl group you would expect to show up in the sort of 1 to 2 ppm region. Now, actually, we're going to talk about something called peak splitting, but we're not going to deal with that yet. So we would expect to see one signal here. These protons that are adjacent to the benzene ring, we would expect to see in the 3 ppm region, and the proton that's, adjacent to the OH group. And the proton that's actually on the OH group, we're not sure where that would show up. It would depend on the situation, but it might show up there. Okay? We're going to see, by the way, that the area beneath a peak in an NMR spectrum is directly proportional to how many protons are represented by that peak. So the CH2 proton and the CH3 protons, the area under those peaks is going to be in a 2 to 3 ratio, reflecting the fact that you've got 2 CH2 protons and 3 CH3 protons. Okay, so in general, in a molecule that's not chiral, CH2 protons are going to be identical to each other, and in all molecules, methyl protons are going to be identical to each other. It gets a little tricky, and this is mostly a preview for your 353 lab where this will become important. If a molecule is chiral, suddenly CH2 protons are not identical anymore. So if we look at this chiral molecule, we got a stereocenter here. Here is an OH group. It's pretty clear to see that this methyl group and that methyl group are distinct because they're in different environments, different connectivity, right? It's also clear to see that this CH proton is distinct from the methyl groups, and the proton that's on the OH group is distinct. What about these 2 protons? We might call them protons A and B. Are they identical to each other? And the answer is, look at the gray box there represents a mirror plane. Notice that the OH group is coming out above the plane, and the proton, the CH purple proton, is going down into the page below the plane. What that means is proton A is close to the OH group, whereas proton B is close to the CH group. They have different chemical environments. and they are different from each other. Now you might say, well, what about rotation? If I rotate around that bond, can't I make proton B close to the OH group? And the answer is only sort of, because if I rotated around that bond, I could put the methyl group here, and then I would have proton B and here and proton A there. So yes, now proton B is close to the OH group, but look, the methyl group's in a different place. You can't ever make those two protons equal to each other by symmetry because of the presence of this stereocenter. So we're going to see that CH2 groups in chiral molecules are not the same, and they can have different chemical shifts. That really isn't going to play much of a role in the kind of problems you're going to get from me in this class, but it is going to play a role in 353. Two CH2 protons that are in a chiral molecule are called diastereotopic for reasons that we don't need to talk about, but you will hear that term in the future. Okay. Questions so far? Different kinds of protons. Okay, so yeah, go ahead.
So do the two hydrogens need to be like adjacent to that chiral center, or can they just be anywhere in the molecule?
Great question. Do they need to be adjacent to the stereocenter or just anywhere in the molecule? Anywhere in the molecule, but the closer they are to the stereocenter, the more likely that their chemical shifts will be a lot different. Further away, they're technically non-identical, but they might on accident have very, very similar chemical shifts. Okay, other questions? Yeah?
So if there's a molecule that has any chiral center, there are not going to be any hydrogens that are the same?
In a molecule with a stereocenter, CH2 protons will not be identical.
Okay.
Yep. Methyl protons will always be identical because you can exchange their position through rotation. All right.
But in that case, they wouldn't, right? Because it's right next to the OH. A little bit closer.
Yeah, these two are the methyl. What I'm talking about is the individual protons on a methyl group. So all of these three protons are identical. These three protons are identical. But yes, they are not the same as each other because of the different connectivity. Yeah?
The chain was a bit longer, so you had CH2 protons just a bit farther away.
So yeah, what if, excuse me, clearing my throat here. What if our molecule was like this? Yes, you would still technically say that each of these protons on CH2 groups are not identical to each other. Now, the question is, how not identical would they be? And the answer is that likely the closer you are to the stereocenter, the bigger the difference in chemical shift between your CH2 protons. But yes, technically these two are not identical in the same way that these two are not identical. In practice, the extent of difference in chemical shift between these two CH2 protons can change depending upon context. Again, you're not going to really encounter that from me, but you will encounter it in 353, and it's one of the more difficult concepts, so I wanted you to be introduced to it here. Yeah?
So with that, would you just have a bunch of small peaks?
So would you have a bunch of small peaks? Yeah, you would see a 1 proton peak for this proton, another 1 proton peak for that proton. Yeah. Okay, so far we've got different, NMR will tell you how many different kinds of protons you have, and it will also tell you something about chemical environment based on chemical shift. So far, though, that's not enough to get connectivity. So we need to introduce a couple of more things, all right? So what I told you earlier is that the area under the peak is proportional to the number of protons that that peak represents. So here, for our example, we have a methyl group peak and then a CH2 group peak. And measuring the area under a curve is either a cut and paste and weigh problem. You can actually print this out on paper, cut the peak out, weigh it on a scale, and then do the same thing for the other peak. Or you can do calculus, which we don't want to do. The computer does this for us, okay? And so what you will do when you see an NMR experiment, you will often see these curved lines. That represents an integral. But you can forget about that word. It just, the distance from the top of the line to the bottom of the line is proportional to peak area. So you're not going to have to, and there will be some number usually that the NMR experiment prints out that's related to arbitrary peak area units, which we don't care because it's all about, we don't care what the units are, it's just all about relative peak areas. So suppose we do this one and we measure that this peak is worth 60 arbitrary peak units. And we do the same thing for that curve, and we see that this one is like worth 42.5 arbitrary peak units. That would tell us that the ratio between these two peaks is roughly, and this is, people are very uncomfortable with this because you want exact numbers. Oh dear, did we seriously run out of apple pencil juice? Okay. We would look at those two integrated peak areas and we would conclude, okay, it's roughly a 2 to 3 ratio in that peak. And very often these numbers aren't going to be exactly 2 to 3. That's okay. Close enough, close is good, like round down or round up, and sometimes you have to play with a couple of different possibilities. For example, this might have been 59, or it could have been 67. You just sort of have to squint and look at the best ratio you can get, understanding that in organic molecules, groups of protons usually come in 3 or 2 or 1. Okay? Now there are times when they come in other varieties. For example, if you had a molecule like this with a T-butyl group, what would I expect the relative ratio to be between these protons, which are identical, and these? It would be sort of 9 to 2. So that's sort of how you use integrated peak area to determine how many protons each peak represents. So that's useful because that can tell you, is this peak a methyl group or a CH2 group? Does that peak represent a T-butyl group? Does that peak represent a benzene ring? That's now useful. But the final piece we need is connectivity. In other words, I don't just need to know that this CH2 group is a CH2 group. I also need to know what it's next to. And that is the concept of what we're going to call spin-spin splitting. And this is a difficult concept. So we'll try to introduce it, and I don't know why I did this last time, but we'll try to introduce the concept of spin splitting. We have an organic molecule with proton A and B. And proton A is Anakin and proton B is Sheev the Senate Palpatine. I am the Senate, right? Okay, so there are two, as I told you before, protons in the presence of a magnetic field can either be aligned with the magnetic field or against the magnetic field. And I told you that the population of those two options is about 50-50. So in any given molecule, Anakin can experience either Palpatine being aligned with the field or against the field. It's got two different options, right? And if Palpatine is aligned with the field, then Anakin is going to experience the external magnetic field plus the field generated by Palpatine. If Palpatine is aligned against the magnetic field, then Anakin is going to experience the external magnetic field minus the influence of Palpatine. So there's two different situations that occur on average 50% of the time. So in 50% of your molecules, Anakin will experience this. In 50% of your molecules, Anakin will experience this. And that difference in environment is enough that when we do the NMR experiment and we look at chemical shift and we look at the proton, the Anakin proton, HA, he will actually experience two different environments. We will see a peak here and a peak here. And because 50% of the time Anakin experiences this environment and 50% of the time Anakin experiences this environment, we're going to see the signal for Anakin split into what we will call a doublet. And it's a 1-to-1 doublet in the sense that these peaks have the same intensity. They're copies of each other. If you integrated the area under the peaks, it would be 50-50%, okay? The extent of the splitting between those two peaks is called coupling, and you can measure that in frequency units of hertz, and that distance between the two peaks is called a coupling constant. It's called J coupling for whatever reason, and it's the coupling constant between protons A and B. And interestingly, if we go to the other proton, if we measure the spectrum, if we measure the chemical shift for proton B, which might be in another part of the spectrum, it too is going to be split into two signals, because it too experiences two different environments, one in which proton A is aligned with the field and one in which proton A is aligned against the magnetic field. And again, you're going to see a 1-to-1 doublet. And you can tell that protons A and B are coupled to each other because they will have the same coupling constant. The coupling constant between B and A is the same as the coupling constant between A and B. Okay? So if you see a peak split into two, a 1-to-1 doublet, that means that proton is adjacent to one and only one other proton. Right? Do you see how that's useful? Now I know something not only about proton A, but I know something about proton B or whatever's next to proton A. Okay, questions about that? That's a pretty challenging concept to get. It's straightforward. It's more straightforward when when you only have one proton adjacent to another proton, but naturally there are more complicated situations. Yeah?
If there was a more electronegative atom closer to one of the protons, would that affect the 1-to-1?
If there was another electronegative atom close to one of the protons, would that affect the 1-to-1 ratio? No, it would affect the chemical shift where these protons are, but it would not affect the splitting. One other question that I think people ask is, how do you know whether two peaks are from the same proton because of splitting or whether they're just two peaks with different chemical shift? And the answer is that this distance between protons this splitting distance is usually pretty small relative to differences in chemical shift. So usually two distinct protons, let's put protons A and B on a larger spectrum. Proton B, let's say, has a higher chemical shift. Here are the two signals for proton B. Proton A has a lower chemical shift. Here are the two signals for proton A. They are, this is a doublet over here, and this is a doublet here. Usually these coupling constants, the splitting between two peaks that represent the same proton, are going to be much, much, much smaller than differences in chemical shift between chemically different protons. Yeah?
Just like, what I'm thinking, we're looking for two like really close together peaks.
Uh-huh.
And that tells us that there's two adjacent hydrogens.
If I look at proton A, the fact that I see this doublet tells me proton A is adjacent to one and only one other proton. Yeah. Similarly, if I look at proton B, I say, okay, it's a one-to-one doublet. That means proton B is adjacent to one and only one other proton. And then if I measured this splitting difference, and if this one was identical to this one, I'd have a good case to say that proton B and proton A are adjacent to each other.
So it wouldn't split if it was next to like other groups or.
So the question I think is related to how far away can these protons be from each other and still split?
Well, just the comment you said that this indicates it's next to the one and only one.
Yeah. Let's talk about what I mean by next to. These coupling constants are usually for being adjacent to each other within 3 bonds or less. Yeah, go ahead.
So if like, you see how those other groups are marked out as like going, so if like one of those groups was a carbon with all its own hydrogens.
Then proton B would be split by more.
So it wouldn't be able to make a doublet because you said it had to.
The pattern would be more complicated because proton B would be split not only by proton A, but by these other protons.
Okay, so it just kind of.
So we'll talk about those situations. It obviously can get more complicated than we're prepared to deal with.
Okay.
Yeah.
So when looking at like the integrated area under the curve, like for the number of protons,
Yeah.
you would just do like, you wouldn't do like all the splits?
So what you can, I mean, you can ask the computer to do that, but most often you would just
All that.
yeah, you would know
That still represents one proton.
exactly. Yep. They are having more fun than you. All right. Yes.
So with an ethane, each hydrogen would be split by each other hydrogen?
Okay, so in ethane, each hydrogen would be split by each other hydrogen. That sounds good. One rule of proton splitting is, and this has to do with physics, identical protons don't split. So actually in ethane, both of those methyl groups are identical by symmetry, so you would just see one peak.
So both,
Okay.
so the previous problem, both those, like the groups we're ignoring, those have to be different from each other.
Exactly. In this isolated example, the groups that I've scribbled out would have to be different from each other. Let me give you some common splitting patterns of functional groups that you will encounter. Okay? So a classic situation would be okay. So orange, purple, blue. In terms of the spin splitting, and sometimes that's called multiplicity, methyl group protons are not adjacent to any other protons. Okay? The other protons in the molecule are 1, 2, 3, 4 bonds away, and normally splitting occurs for protons that are 3 bonds away or closer. So we would expect this methyl group to be what we'll call a singlet, a single peak, and we expect it to integrate or to have an integrated peak area that represents about 3 protons, right? We could also say because it's adjacent to a carbonyl, we expect it to have a chemical shift around 2 ppm. All right. Purple protons are adjacent to 3 other protons. Now this situation is complicated. You've basically got purple protons here on the same carbon, and they are adjacent to blue protons 1, 2, and 3. And again, remember, each of those protons can be either up or down with respect to the external magnetic field at a 50-50 ratio. So this is a probability problem. What combinations of spin can you expect to see? And actually, the solution to this is sort of Pascal's triangle. You ever learned about that? 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. Vaguely? Okay. Let's just figure out if we have 3 protons adjacent to our purple protons. Let's just draw all the possible combinations of spin or of proton spin alignment that we can experience. There would be, and we'll think about how many ways there are to have each of these. So how many ways are there to have all 3 spins aligned in the same direction up? Yeah, there's just only one way to have that. Number of ways, 1. How many different, yes, we know it's very low. How many ways are there to have all the spins aligned down? Just 1. How about 2 up and 1 down? Well, let's see, I can do that, or I could have up, down, up, or I could have down, up, up. Is that all we got? Yeah, 3. Same thing to have 1 up and 2 down. We've got 3 ways to do that. And so, because there are 4 distinct environments that purple proton can experience, we expect purple proton to be split into a 4-line pattern or a quartet, and we expect the relative intensity of those peaks. We expect the relative intensity of those peaks to be 1 to 3 to 3 to 1. In other words, if we were to zoom in on purple proton, we would see a peak that looked like this. And the distance between each of those peaks is the coupling constant. If we call this proton B and C, this would be the coupling constant between B and C. Okay, you'd expect a quartet pattern. A 4-line pattern tells you there are 3 identical protons adjacent. Yeah?
Is every 4-line pattern going to look like that?
Is every 4-line pattern going to look like that? This is the way a quartet, a 1 to 3 to 3 to 1 quartet looks like when you have protons that are adjacent to a methyl group. Yep. Right? Yeah.
2 hydrogens means they're going to be like basically double height, indicating that there's 2 of them.
Right. So the fact that this would integrate for 2 hydrogens. So if we did the NMR spectrum for, we said in terms of chemical shift, we expected around 2 ppm. So we would see a single line pattern for the methyl group, and that would integrate for 3 protons. We would see at similar chemical shift, because again, being adjacent to a carbonyl puts you around 2 ppm, we would expect a 4-line pattern here that if we integrated it, it would be 2 protons. And then based on what we've talked about, let's talk about proton C. It should integrate for 3 protons. Its chemical shift should be around 1 ppm. Proton C are adjacent to 2 other protons. If you're only adjacent to 2 other protons, that gives you 3 different possibilities. Right? You can either be aligned all with, all against, or 1 with, 1 against, or 1 against and 1 with, right? Do you see those 3 different situations? So you expect a 3-line pattern for being adjacent to 2 protons, and it would be a 1 to 2 to 1 triplet. So we would expect to see for methyl group C, a 3-line pattern. And here's where the NMR spectrum is going to give you redundant information that's going to confirm what you are learning. For example, we see the quartet here. That should tell us that protons B are adjacent to a methyl group. We see a peak over here that integrates for 3 protons, and it's a triplet. That tells you that's a methyl group adjacent to a CH2 group. Do you see how those two fit together? We now have both elements in the pattern. We now know about proton B, and we know that protons B are adjacent to protons C. All right. So it does get more complicated than that, but that's going to be enough to be getting on with in terms of solving problems. So let's take a few minutes, and then we're going to come back and we're going to actually just solve NMR problems for the rest of the time.